sklearn, linear model, ARD regression. Description: ARD regression implements a Bayesian linear regression with automatic relevance determination (ARD). It is designed to handle high-dimensional data and automatically identify irrelevant features. ARD assumes a prior distribution over the weights of the linear model, encouraging small weights for irrelevant features and effectively shrinking them towards zero. This leads to a sparse model, effectively performing feature selection. Inputs: X. The input features independent variables of the data as a 2D array of shape n samples. N features. Y. The target variable dependent variable as a 1D array of shape n samples. Outputs: Core. The estimated coefficients of the linear regression model. It is a 1D array of shape n features. Intercept. The estimated intercept of the linear regression model. It is a scalar value. Steps: Initialization. The model initializes the prior distribution over the weights. The prior is assumed to be Gaussian with a zero mean and a variance specified by the alpha-1 parameter. Optimization. The model then uses an iterative optimization process, typically using the expectation maximization M algorithm, to find the posterior distribution over the weights. Prediction: Once the posterior distribution is found, the model can predict new target values based on new input features. Metrics: Mean squared error MSE, the average squared difference between the predicted and actual values. R squared, the proportion of the variance in the target variable that is explained by the model. Log likelihood, the likelihood of the data given the estimated model parameters. Visualization plots. Feature importance plot visualizes the estimated weights of the model, highlighting the importance of different features. Residual plot plots the difference between the predicted and actual values to check for patterns or trends. Prior and posterior distribution plots visualizes the prior and posterior distributions over the weights, showcasing the impact of the data on the model. Fine-tune parameters. Alpha-1, the prior variance of the weights. A higher value indicates a stronger prior belief in small weights. Alpha-2, the prior variance of the noise term. A higher value indicates a higher belief in noisy data. Nitter, the maximum number of iterations in the optimization process. Toll, the convergence tolerance for the optimization process. Uncertainty methods. Bayesian inference. ARD regression is a Bayesian model, allowing for the estimation of the uncertainty associated with the predicted values. Credibility intervals. Bayesian methods can be used to calculate credibility intervals for the predicted values, providing a range of plausible values. Challenges and fixes. Challenge 1. Slow training. The optimization process in ARD regression can be computationally expensive, especially for large datasets and high-dimensional feature spaces. Sample use case training a model on a dataset with millions of samples and thousands of features may take a significant amount of time. Fixes. Reduce the number of features. Feature selection techniques can be employed to reduce the dimensionality of the feature space. Optimize the hyperparameters. Experiment with different values for alpha-1, alpha-2, nitter, and toll to improve training speed. Use a different optimization algorithm. Consider using alternative optimization algorithms like stochastic gradient descent or coordinate descent, which may be faster for large datasets. Challenge 2. Overfitting. ARD regression, like other Bayesian models, can overfit the data if the prior distribution is too weak or the training data is noisy. Sample use case training a model on a small dataset with high levels of noise may lead to overfitting, where the model learns the specific noise patterns rather than the underlying relationships in the data. Fixes. Increase the prior variance. Increase the alpha 1 and alpha 2 parameters to strengthen the prior belief in small weights and less noisy data. Regularization. Consider using additional regularization techniques, such as L1 or L2 regularization, to further constrain the model complexity. Cross-validation. Use cross-validation techniques to evaluate the model's performance on unseen data and identify potential overfitting.